morning, everybody, and welcome to HEXACON. Welcome to my keynote entitled Code in the Wild, talking about exploits. I'm going to talk about the past, the present, and the future. So who am I? I'm a tiny little exploit hunter within the Google Threat Analysis Group, TAG for short. But instead of talking about myself, let's talk about Google, and let's try to understand the reason why Google is so obsessed about exploits and zero-day. So for that, we need to go back in 2010, where we publicly admitted that we got popped by the Chinese gov. This is widely known publicly. What is not so well known is the entry point. The entry point was a one-time link that was sent to an employee on MSN, and that one-time link was delivering a zero-day against Internet Explorer. So after that, you could go and talk to Sergey and Larry, who are the owner of Google, and you can ask them for resources to find exploit in the wild. So that's what we did. So the reason why I'm here and why did I say yes, I think it's been 10 years that we are finding 0 days every year, pretty much. And every time you find the 0 days, you have people on the internet that are speculating on how the 0 days are getting found. And usually these people are wrong. So after 10 years, I guess it's time for me to share back how these exploits were actually discovered for most of them. One slide about ethics. I'm not here to give you any advice about the use and creation of 0 days, but what I wanted to say here is that all the exploits that I will show in these slides are exploits that have been used against persons that should not have been targeted, in my opinion. And the reason why I'm saying that is this thread on Mastodon, saying that the TLDR of the thread is saying that the research that Google Tag is publishing together with Citizen Lab and Amnesty is actually used to identify mistakes that might have happened in the past. So with that keynote, I hope we're going to identify a few more mistakes. So the plan for today, I will not give you an overview of the zero-day industry. I guess you know it better than I do. Instead, I will talk about how the exploits are actually discovered. I will talk about what's happening right before the exploit is delivered to the target. I will talk a bit about the trends we see in the exploits. I will also quickly touch on the post-exploitation part, and then I will give you some thoughts about the future. So okay, let's start with the discovery part, how we are discovering exploits, and a tiny bit of our secret sauce. Let's start with watering hole, motivation. I joined TAG in 2014. I'm sitting at my desk at Google reading the news. I see a bunch of security companies finding 0 days just by looking at watering hole, so legit websites that got compromised. And I'm like, I'm working at Google. We have the whole index of the internet internally. If there is a company that should find this watering hole, it should be us. So I build a lot of systems that are trying to use the data we have internally to find this watering hole before anybody else. And it worked. So instead of explaining the details, let's have a look at an example. Let's work with Uncle Kim to actually find the first Chrome 0 day in the wild that we have found. So basically what we do, thanks to self-browsing, thanks to the Google index that we have internally, we can scan websites over and over and over again, and we can actually do some snapshot difference to see if something happened on that website. Here you have dprkmedia.com. We know that website might get compromised at some point, so we do a scan at T-1. We record everything that happened. You see it's pretty much a static website, only content from dprkmedia.com and just a tiny Google Analytics scripts. So that's zoom. If you do it the next day, you do it again, can you spot something wrong with the content that was fetched? Of course, you can see that there is a new iframe pointing to a new domain that we have never seen before in our Google internal systems. So that's already enough for me to get an alert and to have a look at what was the content that was delivered. Turns out it was the first Chrome 0 day that we have found in the wild. Next example is a set of watering hole that we have found on Chinese-related websites that we are delivering exploits for iOS. And what happened is pretty much the same. We have analysis of this website that is continuous, and then at some point we detect this weird-looking iframe pointing to IPs directly, and the web server is listening on a port that is a very high port, meaning that maybe the web server is compromised and hosting some exploits. So what we have gotten here is a landing page together with Safari, WebKit RCE, and the Sandbox escape. So that is our system crawling the internet that got everything like that. And our system is not using iOS. They are using Chrome. They are just spoofing the fact it's iOS. But we have gotten all the exploits anyway. And the good thing about that one is that if you spoof the iOS version, you get different exploits. So my goal was to collect all the exploits like Pokemon. And I got some hints from the Sandbox escape. So the Sandbox escape, they had one huge function trying to resolve a bunch of APIs. And I realized that these APIs, they were not actually using the exploit itself, but turns out they are using the other exploits that they have for the other version of iOS. So I knew when I have all the exploits that they have. And the interesting part about that one is that if you use a very old version of iOS, you get the exploits completely in clear. If you increment a little bit the version, you get some obfuscation on the JavaScript. And then if you use a version that is close to the latest version of iOS, you get the exploit encrypted with a framework that is open source, Iron Squirrel. So that is not an issue for me because it's a watering hole. The exploits are delivered over and over and over again, so I can decrypt the exploit when they are delivered. But what it tells me that they have something to hide within the exploits that are encrypted. And turns out, yeah, we found a few Sandbox escape and LPEs that were 0 days. Next thing that we are monitoring, it's typo squatting domain. I'll go briefly on that one. It's simply things like that. So the watering hole that we have found just before, if you would go on tipcity.net, you would go serve the same iOS exploits. So that's a technique that is not widely known that we still see nowadays delivering 0-day exploits. Detection, so that's where we have maybe our secret sauce. As I mentioned, the iOS exploits, the first ones, they were completely delivered in clear. So that's a good example for me to show you what we can detect and what we use to detect exploits in our pipelines. So first of all, you have the macro binary that is encoded in JavaScript. That is something that you can easily detect, either statically or dynamically. If you have a variable that is containing an array, and that array contains a MZ, elf, or macro header that is suspicious, so that's easy to detect. Second, you have the garbage collection function that most of the exploits for browser are using, and they all look the same. It's a big for loop with allocation of something that is not used anywhere else over and over and over again. So you can also build detection based on that to identify garbage collection function. Then usually you have all these utility functions that are used to convert numbers from double to integer and vice versa. The good thing about this function is that they are so tiny that you can isolate them from JavaScript and you can call them with expected inputs and expected outputs to find this function. Lastly, also, when you have an exploit, you need to know the exact version of the browser that you are targeting. So that is something that all the exploits are pretty much doing, trying to collect the exact version and trying to have some specific offsets, specific code path based on the version. And lastly, maybe for that one, it's a bit special. So the bug that is used is a JIT optimization issue. And they usually have this type of pattern. So you have a function that is called over and over and over and over again in order to get the function optimized. And then you have one parameter that is changed. And then you have the same function that is called once. So that means that, yeah, you have a JIT compilation issue. So that's good for detection, but that's also good for me. When I receive the exploits, I need to quickly identify if it's a 0-day or not, so I need to isolate the trigger, and thanks to this detection, I can quickly spot where is more or less the trigger. So that was all the exploits. To give you an example of a more recent one, here is one from GPRK from 2022. The exploit was delivered like that. Obviously, it's obfuscated with a framework, but once you decrypt all the layers, that's what you get at the end. So you see the same thing, the get version to get the exact version of Chrome. the garbage collection function that is allocating a string over and over again, and that string is not used anywhere else. And the RCE shellcode is also something that we can easily spot with the assembly, like the ret instruction at the end and the call at the beginning. Okay, let's talk about one-time links now. That's where we are also finding a lot of 0 days, so you need to have a pretty good visibility. So what it is, it's links that are delivered to the target. They are bound in time, and they are delivering exploits only once. So what you need to do as an exploit hunter, you need to be faster than the target, and you need to click on the link before they do. A good example was from last year, like the threat actor was actually sending one-time links directly on social media. They were visible to anybody. So as an exploit hunter, you can monitor for these links on social media, and you can have a pipeline to click on the link before the actual target. Let's talk about crashes now. Obviously, we collect crashes from Chrome, Android, and we try to find exploits from these crashes. And I will tell you the truth, it's very hard. We get millions of crashes, and finding actual exploits, crashes that are coming from exploits is actually a real challenge. But we try, with Project Zero, we try to come up with some logic and heuristics to find crashes that might have happened from an exploit. Here is one example that might be from an exploit. So here what you see is a stack trace from Chrome. So you see a new thread that was created. The entry point for that new thread is outside of the regular Chrome modules that are loaded. So that means that either an exploit managed to load some code in the memory and get to start a thread on that, or it's maybe a third-party app that is injecting code in Chrome that crashed. Second type of crash that we are monitoring are the crashes that are happening more or less between the trigger and the setup of the exploit primitives. So usually you have your trigger, and then you need to set up the exploit primitives. And if you have the garbage collection that is triggering in this time window, then it will likely crash because your JavaScript heap is corrupted. So we are monitoring this type of crash. This is an example of one of the crashes that you can get. But as I said, we get many of these crashes, and it's very hard for us to actually find exploits. But we did. I guess it's time to give you the background on this Pony Award that was mentioned by Renaud. So yeah, we got the Pony Award for apparently shutting down a counter-terrorism operation, and the entry point for that was actually crashes. So what happened exactly? Together with Project Zero, we identified 2 suspicious crashes that are pretty much the ones that I showed you. By themselves, we cannot do much, but what we know is that 2 suspicious crashes from 2 different client ID crashed, and the crash came from that domain. So that means that domain is probably related to the crash. So what we do, we take that domain, we look up on what we have in our data, and turns out we have just one hit. One hit is from safe browsing. Safe browsing automatically crawled another website, which is obeydinsupporters.com, and safe browsing got redirected to that domain where we have seen the crashes. So we went to that obeydinsupporters.com website. That's what we have gotten, a logging page for a non-cloud instance. So that is a file sharing platform. Pretty much you can host your own Google Drive at home. And what happened is that you get this logging page, but also if you go on Android, you get served an iframe that will redirect to the domain that we identify from the crashes, and you get served Android exploits, 0 day. If you go on Windows, you get redirected to another domain that is stats.obeydinsupporter.com, and you get served Windows 0 days, exploit 0 days. I didn't have the screenshot when I created the slides internally, so I went to Google to ask if somebody has a screenshot of this website, and turns out there is an evaluation in any run, so that's a malware Sandbox evaluation, and that evaluation actually got also redirected to the Windows exploits. Quickly pivoting on the domain, we found another instance. Same thing, another instance of OnCloud, easy-to-share-files.com, that was the website. And same thing, if you go with iOS, you get served iOS 0 days, even though it was just the looking page. Okay, now it's time to talk about public repositories. So I mentioned AnyRun before, but we do look at public repositories such as VirusTotal, Census, Shodan, all the tools that are gathering data from the internet. I will give you an example of Census. I gave an example about a 0-day that I found in VirusTotal in my keynote at SSTIC, so I will use another one. So here you have Census. Census is scanning all the IPs in the world, trying to collect banners from all the ports. Here you have a banner from the port 6666. You might not recognize the bytes, but if you dump these bytes into a file, if you open that file in IDA, what you get is a very nice ARM 64-bit shellcode that is called the SOLoader payload. So that is a shellcode to load a SO library in memory and execute that binary. What is very good for us is that that binary is actually in the shellcode itself, so you can also look at the binary, which is the exploits. Turns out for that one, it was a vulnerability that was already fixed in Samsung, but the vulnerability was in the MFC charger that you can only access via radio, so that we suspect was part of a zero interaction exploit chain. And that is good because usually at Google, that's not the exploits that we get to see. Okay, no more discovery. I don't have enough time to talk about all the things we do, but we also monitor for man in the middle. We also monitor for suspicious ads. We also monitor for APK or iPhone applications that are actually using 0 days to elevate their privileges and things like that. So now let's talk about the delivery, what's actually happening right before delivering the exploits. Obviously, you have a lot of fingerprinting that is going on. So when you serve exploits, you need to make sure that you are targeting the proper device or you are targeting the proper person behind the device. So we suspect there is a lot of server-side fingerprinting. It's a bit of a black box for us, but we can guess what they are actually doing. It's pretty obvious. You can fingerprint pretty much at every single protocol level. So you can fingerprint on the TCP level, you can fingerprint on the SSL, HTTP2. So the goal is to identify a proxy that is between the browser and the server. So for example, sometimes to break the ACDH encryption, you need to inject JavaScript. So the goal is to detect that. I'll just give an example of HTTP2. If you use HTTP2 on Chrome, like the handshake, they have multiple settings. These settings are hard-coded. If you use man-in-the-middle proxy, it's written in Python. They use the HTTP2 library of Python, and the library has completely different settings on the handshake. So it's pretty easy to detect man-in-the-middle proxy with that. Okay, now let's talk about client-side fingerprinting. That's where we actually see the disgusting JavaScript and WebGL. Usually, this part is actually larger than the exploit itself. So they are trying to do so many things to try to fingerprint the device. I will first talk about the user agent reduction. So when you serve an exploit, you need to know the user agent. You need to know which browser you are targeting. You need to know the version also. And there is this effort in Chrome or in the web space to reduce the amount of information you get from the user agent in the GET request. So now what is needed is that you need to use the user client ints. And so that is an API that you can ask the browser to give you information. So you can do that server-side, or you can do that from JavaScript. This is an example from the server side. So basically, you need to, as a server, you need to reply with an accept-ch header, and you list all the things that you want to have from the device. And if the device complies, it will reply with this information, which is pretty good for when you want to deliver an exploit, because you get the version of Chrome, which is nice, but you also get the Android version. So maybe if you know that the Android version is old enough, then maybe you have an exploit chain that is generic, so you can know in advance that your exploit will work. And if it's not the case, you also have the device model, so maybe you can have an exploit specific to the device. And if you don't have exploits, you don't have to send any exploits, so that's pretty good. But that's also good for me, because I can also detect when the server is actually asking for all this information from the device. Next, let's see some example of JavaScript that we see. So that's an example. You can probe at the battery API. It's an API that is available to all websites, no user interaction. So basically, you can deduce if the phone is currently plugged. you can see the percentage remaining on the battery. And as you can imagine, when we are hunting for exploits, we have multiple phones, they are all plugged, so that's an easy way to detect us. Same thing, if you compile your own version of Chrome, you need to know that some of the video codecs are not enabled for some licensing issue. And this is also something that you can easily probe. So if you have a codec that is not there, it's very likely that it's a custom version of Chrome that you are talking to. The DevTool console is also something that they are trying to actively probe. And then you have all these variables that if you emulate a version of Chrome, then you need to make sure that they are properly set. Okay, let's talk about the trends in the exploits that we see. This is a reminder of the typical exploit chain that we usually see in Google Tag. So you have a renderer RCE, then usually you have a pack bypass, or a V8 IP sandbox bypass that is used. Then you have the proper sandbox escape for Chrome or WebKit. Then you have a privilege escalation. Then you need to bypass all the kernel protection that are there nowadays, such as RKP or Knox on Samsung devices. And then you get root. What you need to know is that at every single stages, you have access to more information about the phone. And of course, at every stage, they are doing some more fingerprinting. So for example, after the renderer RCE, you get access to some part of the file system, and you can see if, for example, if the phone is rooted or not. And the fingerprinting that I mentioned just before is just the fingerprinting that is done before delivering the renderer exploits. Okay, let's talk about the trends. On the browser side, on the RCE side, I would say the public and private research are more or less on par. We see a lot of exploits against V8s that are public, and those exploits are the same that we see from the 0 days that we are getting. The only change, I would say, is the obfuscation. On the left side, you have the first Chrome OD that we found in 2019. On the right side, you have an exploit that we have found, I think, last year. So you clearly see like they added a lot of obfuscation, and yeah, that's the only evolution that I see. And it's not a big issue for us. That's the example from the iOS watering hole, where I mentioned that they were adding encryption, obfuscation if you use a recent version of iOS. I think we have collected enough exploits that are unobfuscated that it is not very easy, but it's easy for us to do the porting of to deobfuscate the exploit manually, pretty much like you can identify the constant, you can recover the module names, you can recover the utility function pretty easily. Okay, let's talk about pack and V8 IP sandbox bypass. So on the pack side, what we see is we see a lot of reuse of a single pack bypass that will be used among a bunch of vendors. The reason why I think it's pack bypass are usually very hard to fix, or they are harder to fix than vulnerability, and they usually last a bit longer. And for sometimes you need to have an actual fix that is on the hardware. So a lot of devices are left vulnerable to a very specific pack bypass. On the V8 IP sandbox, I think it's still not mature enough. We still see a lot of public bypass when the V8 sandbox is bundled into Chrome. So it's not considered a security boundary when the V8 IP sandbox is in Chrome. So we see a lot of vendors trying to reuse the techniques that are already public. As an example, I think GitHub Security Lab published about one technique early this year about abusing some DOM objects that are also mapped into V8 that are not protected by the IP sandbox. And we have seen these techniques being used in at least 3 different exploits that we have seen in the wild. So now there is something that I'm calling half day. So what it is, it's pretty much when you have your 0 day that got burned, you are trying to find ways to still use that 0 day. On the RCE side, what we usually see is that the goal will be to redirect to a browser that is using Chromium, but that is using a version that is outdated, such as the Samsung Internet browser. And for that, you have the intents on Android that you can abuse, you can use. And basically, we have found at least 3 0 days that were in the intent 3 0-days intent vulnerabilities that were allowing to redirect from Chrome to Samsung browser silently. So we consider that as a vulnerability. And the good thing, I think, for the vendors is that they can still try that 0-day, and if it's fixed, that will be a silent redirect. But if it's not, the user still has the ability to click on, yes, I want to open that link on Samsung browser. So you still have a chance to get your 0-day side-loaded in Samsung browser. We see the same thing on the Linux kernel. That's an example of an exploit we have found a few years ago that was used as a sandbox escape and LP at the same time. And the bug that they used was a bug that was fixed in the Linux kernel, but the bug was not actually considered as a security issue, and therefore it was not backported in the kernel that are used by Android. And that bug was very nice because it was in the EPOL subsystem, and that subsystem is available from within the Chrome sandbox. So they were using that bug to elevate privileges and break out of the sandbox. So this is probably a unicorn. We haven't seen any other bug like that. Usually when we get a sandbox escape, it's a proper sandbox escape targeting a bug within Chrome. And I will give you an example. I guess that's where the public and private research are not on par. We don't get to see that many sandbox escape publicly. And the ones that we have seen privately are all the same. They all look the same. They all look like that. What you get from the RCE is a huge blob that will embed the libchrome. And in that blob, you have the libchrome plus the part that is actually exploiting the sandbox. So that's what you get, 6,000 functions. And sometimes you get code names. Sometimes you get debug prints that are helping you. But what we do together with Project Zero, we have the tooling to port all the Chrome function using bindiff. And once you do that, then you can easily identify 99% of the blob, the binary. And then the 1% that is remaining are actually the exploits. So they are doing that to talk to Mojo. I think it's convenient if you write your exploit in C++, you get access to all the struct and all the tooling, and then you just need to compile. I guess it's a bit of a challenge to compile because you need to have this version for all. You need to have the blob for each version of Chrome, so you need to compile separately for each version your exploits. But yeah, I think that's how it works. On the LP side, I think on Android we still have this issue that the patch gapping is still pretty large. I think Project Zero blogged about that a few years ago, and it's getting better for Google devices like the Pixel phones, but it's still not true for Samsung, Oppo, and all the other OEM. So basically, what I did, I took the latest Mali GPU CVE from September, and I looked at what we have fixed as of 2 days ago, and it's only the Pixel phones that are fixed to, that are including a fix for that vulnerability. So that means all the Samsung device, you don't need a 0-day to elevate your privilege. You can just use that weaponized exploits for that CVE. On the iOS side, we see a lot of sophistication on the LPE sandbox escape, and I will give you an example of this CVE. So this CVE was already a 0-day when we discovered the exploit, so it was already reported to Apple, not by us. But anyway, we found the exploit. The codename for the exploit was noclip, and we have gotten the symbols from the exploit server, so it's pretty convenient for us when you get that, because yeah, you open in IDA and you have all these function names. That's pretty easy to follow the vulnerability. So you get these 3 sets of function: get buggy page, set buggy range, and get buggy range in 2 different places, in 2 different classes. If you zoom in on one of those, you quickly see that they are trying to do some VM allocation, and then they're creating 2 threads. One is the copy and write thread, and the other one is the pinning thread. So that means that the vulnerability is likely a virtual memory issue or a copy and write issue. And if you scroll down a little bit more, you get to this VM remap, which is more or less, I guess, where the trigger is happening. That to say that they're using this copy and write issue to actually artificially inject heap overflow in the sandbox and outside of the sandbox in a highly privileged process. So they are using this vulnerability twice to escape the sandbox and to get LPEs. And that technique was actually used by Loki in 2017 and documented by Jan Beer in one of the Project Zero blog posts. So my point here is that even though we see sophistication, the public research is still also being used as it makes sense. Okay, post-exploitation, quickly. What we see usually after the exploits is the cleaning up part, and that part is actually where they are removing all the traces. So this was the actual cleanup that was done by the post-exploitation after this no-clip exploits that we have discovered. So you have this pound citizen lab function that is going over a list of directory and files, and what they do, they are just trying to remove all the files one by one. So that's pretty efficient. I guess they got the list from Amnesty or Citizen Lab of files that they are trying to see when they do their forensic analysis, and they just remove all of them. On the implant, this is the implant for this no-clip vulnerability that we have seen. You see, it's fairly not sophisticated at all. It's just a single function trying to exfiltrate all the files from the device, and every time they will try to remove their traces by calling this pound citizen lab function. So yeah, pretty not sophisticated, but once again, that's a unicorn. Usually what we see is very, very, very sophisticated implants that are capable of doing so many things. And the reason why is that if you just look at the number of messaging apps that you can have now on the Play Store, it's more than 200. 10 years ago, it was just 10 of this application. And what happened is that all this spyware, they need to support all these messaging applications. So I think the effort to support all of these applications is pretty insane, because you need to look at all of them one by one. You need to understand how they store the data or they encrypt the data. And not only, for example, if today you manage to compromise my phone, if you want to get access to an email that I sent 2 years ago, it's likely that the email is not, it's unlikely that the email is on my phone. You need to talk to the Google server. So the spyware needs to somehow talk to the Google server, get the email, and send that back to the customer of the spyware. So let's talk about the future. I guess we are going in a future where I guess all bugs will matter, and I don't think we will see that many full exploit chain. I think we will see more and more what we call partial exploitation, where you have exploits that will go as much as they can, and they will access the data that they can. Like, for example, we have seen RCE being used on Safari, and they just stop. They will just collect the cookies and then exfiltrate the cookies. So just one bug is used, so we don't get the full exploitation anymore. I guess we're going to see a shift from browsers that are getting harder and harder to exploit to other apps that are also on the phone. I think I took the example of messaging apps. That's a pretty obvious one, but there are so many other apps that all the people are using that are probably less secure than a browser. And as an example, I took the WeChat APK. I took a look at what was inside. Oops. Took a look at what was inside, and what you get is 180 native libraries. That's pretty insane. Sorry. I can continue. They have 180 native library. I just have 3 slides, so I can just continue. Okay. Okay, WeChat, 180 libraries. One of them is FFmpeg. The FFmpeg version that they use is a version from 2019. And on top of that, they are adding their custom codec, decoding codec. So they are patching FFmpeg from 2019. So you can imagine the attack surface of WeChat. And I have one slide saying that the future is already happening. Like we see vendors switching from browser to messaging app. We did discover one exploit early this year where the exploit was targeting a messaging app as a one-click attack surface, and the vulnerability was in the JavaScript engine that was used by this messaging app. And the good thing is that the same engine is used on iOS and Android. It's a custom one, so you can have one exploit for both platforms. And the good thing is that once you have exploited your single bug, you are within the chat application, so you can steal all the information that was from the user of that chat application. If you want to do the same from Chrome, you need to escape all the way to root, and you need to go down to the... Can plug. But I think the screen, they just... Oh, OK, sorry. I should have done that before. So yeah, the future is already happening. We see the switch already. So yeah, actually, yeah, that's all for this.